So in chapter 16, we're taking a little bit of a different turn here, talking about thermochemistry and the energy involved in chemical reactions. So we're going to be looking at things like heat, temperature, talking about their units, looking at something called specific heat, and then we're going to go into enthalpy, specifically talking about reactions and how to determine how much energy is either lost or gained in a reaction. So let's define thermochemistry. Pretty much every chemical reaction is going to be accompanied by some change in energy. Energy is either going to be given off as chemical rearranges into a more desired state, or we might have to put energy into the system to make it happen in order for that reaction to go. So thermochemistry is the study of those transfers that accompany both chemical and physical changes. So we can actually measure the amount of energy that's absorbed or released as heat in something that's called a calorimeter, which sounds a little fancy, but it's just measuring that heat, and it can be something as simple as a styrofoam cup. We just want something that really does its best to prevent heat transfer to the outside environment, so we can just focus on what's inside what we call the system. In one kind of calorimeter, we might have a known quantity of a reactant sealed in a chamber, and it's immersed in a known quantity of water. And what we can do is measure how much energy is absorbed by the water, and we can just measure the temperature of the water. And from that temperature change, we can actually calculate the heat that was given off in that reaction. So what is temperature? Temperature is really just telling us how much energy, the average kinetic energy, rather, of particles in a sample of matter. We know everything around us. The particles are in constant motion, even though it might not appear that way, but that's what is allowing it to, have a temperature. Because if there was no motion, the item or the body would be cold. It would be so cold that we call it absolute zero. So absolute zero is kind of the smallest temperature that something can have. It's more of a theoretical thing. We get things very close to absolute zero. We super cool them, but we can't quite get that perfectly zero temperature where no molecules are moving. We've gotten close, but it is a known factor, a known value based on experiment, and that value is negative 273 degrees Celsius is what we call absolute zero, the coldest temperature we can record. So to convert between Kelvin and Celsius, we're going to have to add 273 to the Celsius temperature, because Kelvin gives us a more absolute scale. Celsius kind of goes in based on water. Water's freezing point is a zero. If we're negative, we're below zero. We're below freezing. If we're positive, we're above freezing. But with Kelvin, you start at zero, the coldest temperature we can record, and then you move up from there. So let's talk about the units here with heat. Heat is measured in joules, and heat is really just a transfer of energy. All energy, in fact, is measured in joules, not just heat, but we can consider heat the energy transferred between samples of matter due to a difference in their temperature. So if you are outside and you come inside and let's just say you sit on a chair, the chair is going to be warmer compared to your body temperature. You're going to transfer heat to that chair. That's really the transfer of energy is what we call heat. And just note that it always gets transferred from a higher temperature to a lower temperature. So again, you might have an injury, you put an ice pack on it, it feels like that you're getting cold, but really what's happening is the energy is being transferred from you to the ice pack. So it's always going from higher temperature to a lower temperature. So the next thing we want to talk about in this chapter, specific heat. This is why different objects in a room might feel hotter or colder based on the material they're made of. So if you touched a wooden desk, it might not feel as cold as if you touched like a metal faucet. The reason for that, and they actually are at the same temperature if you're in a controlled room. Both of those things will be at room temperature, but the metal object feels colder than the wooden object. That's because of this thing called specific heat. And what's happening is the wood has less ability to take heat from you, to take energy from you in the form of heat, because it does have a high specific heat. Water is the same way. It takes a lot of energy to actually warm water up. That's why it takes a long time for it to boil. So different substances have different specific heat. And specific heat is defined as the amount of energy, so the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius, or we can use units of Kelvin and say how much it takes to raise 1 gram, 1 Kelvin. So there you see at the bottom, I have these two units, joules per gram Celsius or joules per gram Kelvin. You want to make sure you're paying attention that you're in the right temperature for that, because a substance will have a different value for each, and those will be given to you. We have a chart or a table that has those values, and in fact, on the next slide, you can see these ones are given in joules per Kelvin times mole rather than grams. But aluminum, you see, it has 24.2, a lower specific heat, and something like water in its liquid state has about 3 times that much at 75. So you think aluminum tends to be cold to the touch, does not have a high specific heat. Water, on the other hand, we can put a lot of heat into that in order to change its temperature. It would not take, from heating a pan, it does not take long for metal to feel hot once you start heating it on the stove. So let's look at the math, the calculation. How do we calculate specific heat? It is a value that can be determined experimentally. We would just literally determine how much energy I put into a substance and see how, we know the mass of the substance, let's see how much the temperature changes. So it's a ratio between, the more heat I put in, the higher the specific heat. And if the temperature changes quite drastically, specific heat is lower. If the temperature hardly changes at all, since it's in the denominator, specific heat is higher. So a lot of times you actually see it written how it is in the bottom, because we pretty much know the specific heat of most compounds. So we're usually interested in figuring out how much heat it will take to change its temperature, or maybe inversely interested in how much its temperature will change. So a lot of times you see it related down here. Q equals, I usually think of it as mCp delta T, but they have it written there as C times specific heat times mass times the change in temperature. So let's just look at an example problem, then we'll wrap up this lesson here. So this problem here is asking, we have a 4 gram sample of glass heated from 274 to 314 Kelvin. So that relates to a temperature increase of 40 Kelvin, because we went from 274 to 314. and it absorbed 32 joules of energy as heat. So the first thing they're asking us is what's the specific heat? And that can be found by the top equation at Q over mass times delta T. So C equals Q, and by the way, this is the symbol they decide to use for specific heat, but it's Q over mass times delta T. So we're going to have 32 joules divided by, my mass is 4 grams, and the temperature change is 40 Kelvin. So I'm going to take 32 divided by 4 times 40. So in other words, 32 divided by 160. And that's going to come out to give me 0.2. The units are literally just what they are. Joules divided by grams Kelvin. So that's my answer for part A. And then part B, they're asking how much energy needs to raise that glass sample from 314 to 344. So I'm going to set it up as Q equals mCp delta T, or Cp times m times delta T. And it's going to be, we just found the specific heat to be 0.2. We're going to multiply that by the mass of 4 grams, and the temperature raises from 314 to 344, so that's 30 Kelvin. Multiply all those things together, you get 0.2 times 4 times 30. Let me do that calculation real quick. You get 24, and the unit for this is going to be in joules, because we have joules per grams Kelvin. Grams cancel out, Kelvins cancel out, and I get 24 joules is the amount of heat it would take to raise that sample of glass. So that's an example using, finding specific heat, and then using the specific heat to find the amount of heat it takes to raise the temperature. So in the next lesson, we'll talk about enthalpy. This is a good stopping point for section 1.